All right, so last little finalizing part today, we will bring the stuff that we have been doing now for 2 weeks actually together a little bit in terms of looking at the statistical distributions of the normal galaxy population, I call it here. And that is that because in 2 weeks we're going to discuss, well, I don't know, should we call it non-normal? I don't know, active galaxies. And that's not included here. So active galaxies are those which you know host a so-called AGN, active galactic nuclei in the middle, where we have different processes to consider in order to understand them. So we discussed them as a separate class, and now we're talking about the normal galaxies, ellipticals, spirals. So here is the color magnitude diagram, you can call it, about of the galaxy populations from one of these statistical surveys. So classically, of course, what we have done as astronomers is that we have taken, galaxies are very beautiful, so we still photograph them, right? But you know, you take the photograph and you look, okay, is this a spiral? Is this an elliptical? Perhaps you can deduce a luminosity, or a visual magnitude, a color, etc., and you can do that manually. Nowadays, of course, we can do that more routinely with the big databases, such as Sloan Digital Sky Survey, but here is from the Millennium Galaxy Catalog, which is another, and so forth, and then we can get much better statistical constraints. This can even be done in, there are interesting projects, actually, so to say, you can think about it as trying to bridge the classical, more manual approach with new databases. You can look at, for example, the Galaxy Zoo project, which is a very interesting outreach project where you can, it's a big database of galaxies, and any person can actually just go in there, and then you can click on that, and then up comes an image of that galaxy, and then you will classify it. And then there's a statistical thing there, so you will be added, so your classification of that, so if you misclassify a spiral for an elliptical, then it's your fault, huh? In that. No, it's a community project, so the idea there is that statistically, we will actually be quite okay. And then the community can help in order to classify a huge amount of galaxies, yeah? Are they spirals? Are they ellipticals? What type of basic properties do they have? And then we can collect that into databases and then do data mining analysis from that. And quite a lot of interesting results have actually come out that. So I highly recommend checking that out actually and doing a few galaxies. It's pretty fun. The Galaxy Zoo project is called. Anyway, back to this. This is from a research project then, obviously. So here you see the color magnitude, and you can see that galaxies, they're not arbitrarily, randomly occupying the full space, but rather you can see that they are centered here around two groups. So these are contour plots, so it's a denser concentration up here, there's a denser concentration up here, and if you just now put the color there, and the number counts here, then you can see that indeed what you get are two peaks. This is the red and the blue peak, okay? Now you can also see that it's, so this would be like, you know, again, ellipticals are red, spirals are blue type of thing. So here you can see that it is a little bit like that, but there is a lot of galaxies also in between. And for example, our Milky Way would likely be classified as a green valley, as it is called, galaxy here, as just an example. Now you can also see that these peaks, they're actually not entirely at the same visual magnitude. So again, this goes to the fact that ellipticals are actually quite a bit more luminous on average than spirals, and we will see that coming back in these slides, right? So this is how you can use this type of color magnitude and the number counting in order to deduce properties about the statistical distribution of galaxies. So, for example, here is done by in an assignment by an old student in the course. This is with then SDSS data. You will learn how to do this next week. For galaxies with redshift lower than 0.05. So this is more or less the same type. You can see the color plot here in color magnitude diagram, right? And you can see the two clear peaks here, and here you see the blue and the red bump. And you can also see this, what I already said, that, well, red ones are at higher luminosities than the blue ones. It's not at the same characteristic luminosity here, right? So this color map then done by a student in the course is confirming, you can say, the research result here. And then again, this is also the type of diagrams that you will learn how to do next week. Here is another. This is from another old student where so we're going to sort this now. We're going to take this distribution, yeah, and then we're going to sort it along with the magnitudes to see if we can deduce more about, you know, the red galaxies dominate the distribution at high luminosities, and the blue galaxies dominate the distribution at the low luminosities. And indeed, you can actually see this. This is just sorted according to magnitudes, as you can see up here, according to colors, and you can clearly see how the distribution shifts. And at a certain magnitude, you see both distribution, but then as you go, you tilt more to one side, yeah? And this is just a normalized scale to see more. Because, of course, what you have to realize when you do this is that, well, there will be detection issues here. So you always have to sort of say, discuss this and take this a little bit into account, right? That your instrument will only be, or your database will only be able to detect galaxies above a certain luminosity, you know. We have discussed this many times now, qualitatively in terms of dwarf, etc. But that's generally true, right? So below a certain luminosity, you won't see it. So at lower luminosities, you will have lower number counts than at higher luminosities. Yeah, so there will be a certain distribution there. And that is an observational bias that one always have to, so to say, we always have to have it in our head when we interpret these type of data sets. Now, here again, you see this. This is the original that we were trying to re-examine there, data from SDSS, and red galaxies dominate the distribution at high luminosities, as you can see here, yeah, going from the very highest over here. You have a little bit of peak, and you see that the blue components, they come more and more and more and more. Here are more bins, yeah, larger data set, more bins, and you can see that now when you go to the lower, the distribution simply shifts. And you can also see this type of number counting things here, right? Yeah. So blue galaxies dominate the distribution at lower luminosities, red at higher. We can see that. And that goes to that, yeah, okay, so red galaxies are typically, if you have a high luminosity galaxy, it's often a red galaxy. And we sort of, when we have gone through the spirals and the ellipticals, we sort of knew this, right? CD galaxies, for example, they were the most luminous that we knew, and they're ellipticals. And also, if you look at the higher end, they were typically more skewed toward that, right? So here is a full, this now just shows the type of analysis that we can do with this data mining type of things, because here you can also, depending on the database and what has already been done, you might be able to deduce things about the half-light radius or the cutoff radius. Yeah? The Sérsic index, you can see here. This is an interesting plot, for example, where you plot the Sérsic index versus the color. And if you look at this plot here, you can see, well, there is an island there at 1, right? Yeah? It lies at the blue. So disks, exponential distributions, n equals to 1 Sérsic index, blue galaxy, it sort of fits, right? You go to the red, Divoculaires, ellipticals, n equals to 4. Well, yes, but perhaps a little bit more spread here, right? So this one holds up fairly well. This one, perhaps, could we say. Just as one example. There are, of course, many things you can investigate by looking at these type of pairs. Here is this Sérsic index from another database, again, where they do seem to find, you look at the Sérsic index versus the magnitude here, so you do seem to find an island here around the exponential, right? Another island around 4, this is plotted in terms of there, and there in this database, it's a little bit more clear, I would argue, than in this, which is from another database, from another study. And I show you this just as to exemplify that we always have to be a little bit careful when we do the interpretation. Is there a peak around 4 or not? Well, it depends, could we say? So there is, what we can say is that we can easily see from these type of statistical studies where the whole idea of the exponential distribution and the Divoculaire came from, right? But when we look at now better data sets, better data mining, larger distributions, then we need to refine perhaps the picture a little bit, right? That being said, of course, this is also done by a fast analysis of these galaxies. So there are uncertainties associated, quite big uncertainties often associated with how you infer the Sérsic index for these galaxies. And we could also see that when we had the detailed studies of, for example, elliptical galaxies in the beginning of this class, you saw that, well, yeah, you got a certain fit with the Sérsic profile, but it didn't perhaps fit the whole profile. And that, of course, then comes with an association on the uncertainty on the Sérsic index here, right? But large and large, we can easily see here where the classical terminology, the classical Divoculaire law, the classical exponential law come from. Now, here also then, toward the end, I wanted to mention another thing that we can refine, we can call it, the classical terminology, and that is that ellipticals are red and spirals are blue. And if you look to the left here, you see these diagrams, and these are galaxies classified as elliptical galaxies, where I mentioned, for example, how do you do that? Well, you can appeal to the Galaxy Zoo project, or you can do some other things, right? But these galaxies, they have been classified as elliptical galaxies, and then we take their characteristics and we plot them, and we do see that they're red. The vast majority are red. Yeah, so that holds up pretty well. The red, a lot of the luminous galaxies are also elliptical galaxies. So those two aspects, pretty fine. Not all elliptical are luminous, but the most luminous galaxies are normally ellipticals. Now, similarly for spirals, though, we see that they have a much wider spread in color, going from bluish all the way up to reddish, right? So, what can we deduce for this? Well, spirals are not always blue. And there could be many reasons for that, of course. Varying level of star formation, how much gas is there. Could also be extinction issues, Dust extinction and interstellar extinction, intergalactic extinction can play a big role in inferring these. And yes, of course, one tries to correct for that. But how good that is, can vary. Now, what we can say, though, is that we can sort of say reverse the statement, perhaps. So we can say that if you have a galaxy that is blue, it's going to most likely be a spiral galaxy. But not all spirals will be blue. Okay? So if you have a blue galaxy, it's going to be a spiral galaxy, but not all spiral galaxies are blue. That we can pretty safely say from this type of analysis. So in summary then, when we go through that the distribution of galaxies, it's not random in color, magnitude, and related diagrams. We get some sort of color magnitude relations here. And they tend to occupy space along well-defined sequences, as we have discussed, blue sequence, red sequence, etc. But we also have green valley galaxies, likely our Milky Way. Now, many global properties, they're strongly linked to the luminosity or the mass. The more massive the galaxy is, the more likely it is to be red. We discussed this. The more luminous, the more mass, the more reddish. Strong 4000 break, which is one of the Boltzmann feature. To have a large Sérsic index, high metallicity, and a large effective radius. All of this we have, so to say, discussed now during today. And vice versa then, if you have a less luminous galaxies, they're more often blue, not always. They have a weaker 4000 break. They tend to have lower Sérsic index. If you have near 1, then you have the exponential profile, which we have come back to many times now. Lower metallicities and smaller effective radii. So there are clear correlations here, right? We just have to be careful when we interpret this. And like I said, next week you're going to start to explore a little bit of this yourself. Fun with Sloan, we call it, and that's going to be with YPN then. So here's the web page that you can look at. And as a prep, I'd say that just make sure that you get an account, so you don't have to spend next week, just doing those type of things. And you can also have a look perhaps at the previous year's Fun with Sloan on Toledo platform, and that will help you if you want to get better prepared, and perhaps then you can take further steps than you would otherwise be able to do during the class next week.